It's recording now.
It's recording now. Okay, so okay, so let's review a little bit what we'll be talking about during these 4 sessions, so you feel you get an idea if some session is interesting for you or not, and you can skip it or keep it in the background and do something else. So the first day is very introductory, is explaining to you what an HPC cluster does, why we have such machine or this kind of machines in our institution, and how you can access the machine. So that will be the material that we'll be covering today. Very easy access, something very simple. And a little bit of command line interface. So that is something that could be new for some of you. I hope I can devote some time for that section. If you are familiar with this, if you are familiar with Open On Demand, you can skip it. For most part, that will be it. Second day, so this will Wednesday, we will be talking about text editors, so how you edit files, text files on a remote system in the cluster, how you activate and deactivate software that you could need for research, that those are called environment modules. This is one way for activating software, the variety of software that we have installed in the cluster, and how you submit jobs. That's probably the most important section in the most important day will be tomorrow, because most of your actual interaction with the cluster will be with submitting jobs and monitoring jobs and getting the results back. So this is the most important section for that we will see. Day 3 is a little bit more advanced and specialized, is terminal multiplexing, which is an application that allows to have multiple terminals. So when you are operating doing on one terminal, for example, editing files, and another monitoring jobs, and another doing some post-processing, instead of opening one terminal, separate terminal on each for each purpose, you can open just one, and you can split and you can create Windows panes, a variety of things that allow you to work more efficiently, and also to continue the work. If you are working on your office and you just close, go back to your home, you open and you recover everything that you have, and you continue working without disruption. So, and a more specialized a couple of software packages or applications that are very important in an HPC system. One is Conda. Conda is a way of installing software in what is called a Conda environment that offers some sort of isolation from the software that is installed on the host, on the cluster itself, and software containers, which is another layer of isolation, another way of isolating code. Okay, thank you, Dan. For day 4 is even more specialized. Not everyone needs this. It's more if you need to go into developing some codes, so version control, how do you compile codes, how you navigate a little bit the compilers, MPI implementations, and a little bit of shell scripting. So if you feel that your research doesn't need to go that far, you don't need to compile anything or do anything like that, you can skip day 4. Day 4 will be Wednesday of next week. So feel free. That is pretty much what we'll be covering in the 4 sections, in the 4 sessions, 4 days. So that's it. So let's review a little bit before I enter into the more lecture section. I will just give you this so you in the background can try on your own to get access to the cluster. There are basically 2 ways to access a supercomputer like Thornyplat. Let me see. Did I make a mistake? Oh yeah, sorry. It's a mistake. It's a mistake from my side. Actually, yes, it's 10 a.m. to noon. For some reason, I made a mistake here on the schedule. I hope for tomorrow I will edit this. So sorry, Ashley. Yes, it's 10 a.m. to noon. I don't know how. I would probably put the starting time wrong, but yes, it's 10 a.m. And the 3 episodes that's what they are called in this are 40 minutes each. So it's 40 minutes for this introduction. I hope I can get some extra time. It could be a little bit flexible inside each day, but it will be running for 2 hours. Yeah. So before I explain what an HPC cluster is, I will have to go a little bit backwards in explaining this. So there is a machine where we will be using that is called a supercomputer. The name of that supercomputer for us is Torniflat, and there are several ways of accessing this machine. There are basically 2 ways. Either you access with what is called a secure shell or secure remote access, or through a web interface. We will be covering both. Let me explain a little bit. Okay, the easiest one, which is the web interface. With the web interface, you just need to go to this URL that I'm marking here. This URL here, and you will enter your username, your password, and after that your authentication. So you do authentication with your phone. You land into this web application, and from this web application you can open terminals, you can create Jupyter notebooks or RStudio sessions. So you can do a variety of things just from the web interface. So you don't need anything special, and this will work exactly the same regardless of which operating system is on your computer that is in front of you right now. And there is another way of accessing the cluster, which is SSH, or remote secure shell. And the way of accessing the cluster via SSH, it depends a little bit on which operating system you have on your side, on your computer. If you are using Windows, and most likely most people attending this use Windows, you can install one of those 2 packages. One is this one called PuTTY, and the other is, for example, called Mobile Extern. They're not the only ones. There's just a couple of examples of software that serves what is called an SSH client. So it's a software package that you have to install, or at least put somewhere in your computer. There are versions that you don't need to actually install. You just uncompress a folder and you just click on that icon and it will open. When you don't need it anymore, you delete it, and you don't have to go into the nuisance of installing a software and after worrying about having that taking your space on your computer. So this is one software. This PuTTY is very small. This is less than 1 megabyte. This is really tiny. And when you open it, it looks like this. You open a window like this. You enter this address, ssh.hwvu.edu. This is our gateway. This is something that the central IT has controls. It's a machine that allows you to jump into a location inside campus from outside. So it will control the access somehow. And after that, you will have to enter your username, your password, and that will go into your Duo authentication. And after, you land in something like this, something with this name here. So And we will explain later a little bit about command line interface, how you start jumping between machines. And from here, you just execute this, you type this exactly as it is. It needs to be lowercase, it needs to have this space after the SSH, it needs to be exactly like this to jump into the final machine. So there are some security procedures or security steps that you have to do. Is a two-step jump into the cluster, into Thorny Flat, and later on into our newest cluster, Dolly Sauce. It will be exactly the same. So this is the way for accessing with PuTTY. The other application is Mobile Extern. I think I have it here, the link for that. There is a free version, there's a portable version, so it's just a zip file that you uncompress and you execute. You don't have to install anything. And it looks like this. It's a little bit more complex, a little bit more, it has more features, this Mobile Extern. It allows you to export, to open windows from the cluster back into your computer, for example, or getting windows with a plot or an image or something back to your computer. So it's a little bit more capable, but it does exactly the same thing. It has an SSH client. You see here, it's an SSH client with an X server. That's why you can get those windows back to your computer. And you basically execute the same thing. So SSH, go exactly this, as we type here, like here, SSH WVU, and at the end, you jump into the intermediary, the gateway, this machine, and from this machine, you move into Thorny Flat. You know that you are in Thorny Flat because you will see something like this when you log in. This is the name of the machine, the name of our head node, the machine that gives you, that hosts you when you connect to the machine. And here I have more generic instructions how you jump, the double jump to Thorny Flat. So that's one way. And after you jump into Thorny, you first jump into the gateway. The gateway is a machine that the security is secure. They have some security things monitoring what you're doing, how are you jumping from, whether you jump in. It has some security in it, and from there you are actually on a machine that is officially in campus, and from this machine you jump into Thorny through a secure channel. That's it. If you use Mac OS, is super simple because they have all those SSH clients included in the, so you just go into applications, utilities on a Mac, and there is a terminal, and you open the terminal looks like this, and you simply execute SSH, your username, and SSH WVU edu. Remember that this cluster is not only for WVU. People all across West Virginia can ask us for an account, and it's free, regardless if you are from West Virginia, if you are from other universities, and we have some participants from some other universities here in West Virginia. All of them can request an account with us for free. There is not cost for using the cluster. You can just get an account and start executing research, doing research on our machines. No problem with that. So this is part of the conditions for which we got the money from the funding agency to offer this widely for West Virginia research institutions. So so don't worry that you see WVU is because we manage the machine, but it's not exclusively for us. It's for West Virginia as a whole, for research institutions or higher education institutions in West Virginia. So this is the way you access the cluster from a Mac. From a Linux, it's pretty much the same thing. terminals is one icon that is somewhere in your terminal if you are using a Linux machine. And the procedure is exactly the same. SSH, your username at SSH WVU edu. It looks like an email. It's actually your username belongs or at this machine, and this machine will greet you, and from there you can jump into Thorny. The generic instructions are those, so the double jump is right here. So while I start lecturing for the next section, you can take time and review and see if you can jump into the machine with this. And the first thing that we will be doing is open on demand, so we'll give you more time today to use. The idea is that for the next session, so for Wednesday, you are able to access the cluster regardless if you are using SSH or open on demand, or the web interface or the SSH client. It should be possible at that moment. For today, it's kind of optional. If you are in trouble, use the web interface and you can follow me. So let's go for our introduction. This is pretty much a lecture, so you can go in background and exploring a little bit what it is. So I told you Thorny Flat is our HPC cluster. First thing to know is what is HPC and what is a cluster and what is a supercomputer. Well, basically a supercomputer is a computer that today is far more powerful by at least an order of magnitude or something that a normal computer, normal desktop computer, laptop, regardless of how powerful that could be a workstation. And high performance computer cluster is one particular version of a supercomputer. So supercomputer is a computer that is super powerful today. It will not be super powerful in 10 years, but today is an extremely powerful computer. So, far exceeding what okay, and good. Thank you, Nate. That is a supercomputer. Just today, or from a few years, the most popular or the most common kind of supercomputer is an HPC cluster. In the old days, let's say 20, 30, 40 years ago, supercomputers were very expensive machines. So they're expensive at that time. Imagine a machine in the 80s costing $5 million. So today, those machines cost hundreds of millions of dollars. That are built as a whole, as a single entity, and that is a supercomputer. Today, supercomputers resemble more like an aggregation of things that looks like a computer, like a normal computer. We will do a mental experiment to understand a little bit how we build supercomputers today, for the most part. And the purpose of a supercomputer on HPC cluster is to execute high-performance computing. High-performance computing is the use of these machines to execute research that requires an immense amount of computational power. It could be a big, very, very big numerical execution. There are a lot of crunching numbers happening. And if you are not using the machine, either you cannot use it, you don't have enough RAM or enough CPU to execute it on a reasonable amount of time. So it means that you have to put your machine to work for an entire year and hope that nothing bad happens with that computer to get the result. If you use a supercomputer, you can get that in a couple of days or something. If something is taking a week on your normal computer, it could take just 1 hour or less on a supercomputer. That is the idea. There is also a collateral idea that is part also of this, that is called high throughput computing. In that case, it's not because you want to execute something that is so big that it will take a lot of time. It's because you want to execute many, many things. So you don't have enough computers and the management of those computers. So you prefer to use one system to evacuate a number of jobs or a number of executions. So that is, for example, if you are testing, let's say, one simulation under different parameters, for example, temperature under different pressures, or and different solvents or something like that, in chemistry or in engineering or something. You want to test that. So what you have is a bunch of relatively heavy executions, and you want just to evacuate those. So you have a machine that is also capable of high throughput compute, moving those jobs forward and execute those. Let me see. Okay. Okay, good. Thank you, Daniel. So you see, you are getting help from my colleagues, from Daniel, from Nate. With so if you get something, I'm also monitoring a little bit the chat, but you are in good hands. So so let's do an experiment. Let's do a couple of experiments to get an understanding on what an HPC cluster is, and compare that what you have in front of you. So the first idea here is to check a little bit the specifications of your own computer. So here I am putting in these 3 tabs a few ways you can monitor or check or visualize a little bit the specifications of your own computer. So in the case of Windows, you go into this, the control panel, system and security, and the system. And there are a few things that I would like to emphasize. One is have a look at your processor, this. So this line here is the model and the speed of your processor, your own machine. So check that on your own computer and see what you get. And this one, for example, here is the amount of memory that you have. The memory to execute things on the machine is called RAM, random access memory. Check which is the value that you have. Today, this is a very slow value. So most machines today, they have 8, 16 gigabytes, maybe 24 or 32. It depends, but I will say today the range is between 8 to 16. What you get from a modern computer, laptop, or except if you are a gamer or something, you can have something a little bit more powerful than that, but it will be around those numbers. So check those 2 things, and we will see how that compares with a supercomputer. On a Mac, it will be just clicking on the apple on the top left corner, and it says about this Mac if you are using that. This matches all, of course. And here you can see the speed of the processor, a little bit of the spec. It will not tell you exactly the model. You have to dig that in a different way, and the amount of memory. This time, this machine has 8 gigabytes of RAM, this memory for execution. To check that, and also the graphic card. But the graphic card in this case is used for graphics, different from the use that we do in supercomputing. And in the case of Linux, it depends on the distribution you are using. For example, if you are using a particular distribution, for example, Kubuntu, there is a way for getting the system and check the processor and the amount of RAM that you have. So I'm picking a little bit the numbers that you have here from Windows, Mac OS, Linux, 3 different machines. Or if you are using Linux Mint, for example, you get something like this. You get the processor here, you get the memory that you have, and also the hard drives and graphic cards, all that. Okay, so those are different ways of checking that. At least check the most important things that we will be discussing here, which is the CPU, the processor, which is the chip that do all the mathematical operations for most part, putting aside GPUs, they are executed by the CPU. So the model will tell you a little bit how performant it is, and the speed used to be an indication of of performance. Today is no longer the case, so don't pay too much attention today to this. Pay more attention to the model, and we'll show you a little bit how you get more information from there. And the amount of RAM, which is very important. It depends on your research area, but for some people, for example, people in genomics, people doing bioinformatics, they need an enormous amount of memory because they read entire genomes in RAM to process all that as fast as possible. So RAM is extremely important in that area. In chemistry, depends, not at that extent. In engineering, it's cool or not. It depends exactly on the area in engineering where that could be relevant or not. So RAM is something that is also important for scientific purposes, for statistics or machine learning, or it depends on the size, on exactly what you're doing with that. It could or not be important. Just to give you an idea, now you see this, for example, let's check here the specs for the machines here. So you get this. The CPUs that we use on a cluster are very different. So those are consumer level CPUs. So they are intended to be performant or no, i3, i5, i7. They perform better as you move up into the denomination. We use different kind of processor because for us, for this kind of machines, they are intended to run 24/7. So this kind of processors, consumer level processor, are not designed to sustain a load for with such intensity. So we'll probably burn, or it will probably degrade very quickly. So we use a different kind of processor, specialized for being in this kind of supercomputers. They could be a little bit lower in the speed, so we will see that, but they are different. On the contrary, they have many, many cores. In our machine, a typical compute node has 40 core CPU cores, so 40 entities capable of crunching number on a single machine. And we have for most part 2 processors with 20 cores each. So at the end, 40 cores capable of crunching numbers and execute something that in the best case scenario could be 40 times faster. In a very idealistic scenario, 40 times faster that you can do with your own computer. And the amount of memory, we have 4 kinds of machines in terms of memory. And now our definition of a small memory machine is a machine with 96 gigabytes of RAM. That is our definition of a small amount of memory. So that exceeds by far probably what you have on your own computer. And we have just a few machines with up to 760 gigabytes of RAM. So if you need that, you would most likely not be able to execute your job on your own computer. You will have to use a supercomputer like Thorny Black. So now let's review a little bit the advantages of why you want to use an HPC cluster, why you want to use a supercomputer. Well, first is the speed. I told you each machine in the cluster have 40 cores per node, per compute node. So one machine has 40 cores, and we have like 150 machines available on the whole system for all the people that is using the machine. So that, and you eventually can request multiple machines if your job, if your code is capable of using those multiple machines for a single job. We can offer you multiple machines and have 40, 80, 120 or more CPU cores available for a single execution. So that is one advantage of an HPC cluster, a supercomputer, speed. Another is volume. By volume, I mean the amount of RAM and also all the set of capabilities that exceed typically what you have on your own computer. Let's say in our cluster, in our supercomputer, we have like 600 or 700 terabytes of space available, and you can use like 20 terabytes at some point. It will be okay. It's difficult. It may be, but it's not so common that your own computer offer you 20 terabytes of RAM. And also those machines are specialized in the sense that those are not normal hard drives. There are hard drives where the data is spread across multiple physical drives. So it gains in terms of speed and performance and all that. So there are reasons for it. Also efficiency. You are using this machine, and if you use it properly, the machine works for you. The reason why we have this kind of workshops is because these workshops prevent us or offer you a way of not risking yourself being a slave of a machine. So the machine should work for you, no you work for the machine. If you don't have the tools or the knowledge, it could be very easy for you to end up being a slave of the machine, feeding the machine with things instead of the machine working for you, and you just do better things, more intelligent stuff, rather than babysitting or taking care of a computer. That's the idea. So if you manage properly, an HPC will give you time for doing something else, for more important research, for you to use your brain on things that really matters. So the cost, when you put all this machine, it could be costly. A typical HPC cluster that we have, those machines cost around $1 million each, and they last for a few years, 4 or 5 years. We can extend the life a little bit longer, but very expensive. But on the contrary, many people benefit from this machine. The machine receives a centralized management, so the management of the machines is simpler when you consider the volume, and the energy consumed by those machines is lower for the processing that is doing compared with the normal machine that is idle for most of the day. Your own computer is idle. If you leave it open during the night, it's consuming something, but it's basically idle for most part of the day. So that, and convenience, if you use it properly, and that's the focus of this workshop, to learn the tools and the skills, so you use this kind of machine, it could be very convenient to have that, to process that, to launch hundreds of jobs and do something else, and tomorrow, in 2 days, you return, you come back and see the results of that, you aggregate all that. do post-processing of your data, and you create plots that will go into your paper and move on. So instead of executing one job and after waiting for the machine to finish to execute the next one and checking if the machine finished to execute the 20 jobs that you have in front of you. With this machine, you execute everything and the machine takes care of putting those jobs to an execute. In different machines, we have more than 150 machines to execute stuff. So that is convenience. Not everything is better on an HPC cluster, of course. So for word processing, of course, your desktop computer. For reading emails, your desktop computer does a much better job. You don't have internet access on a compute node, for example. So there are things for which a desktop computer serves its purpose. If you are processing very tiny things, if you are using a small statistics, what just say 100 points, 1,000 points, you can do that with a normal computer. But if you grow into a more larger extent or more demanding calculations or simulations, or there is a point where you will be putting these kind of machines too far, and it's better to use an HPC cluster. So that is. So now I mentioned a lot of terminology, and I have to round in this first lesson a little bit of what means all the terminology. So sorry if I go into terms that you don't understand. I need to clarify those, and it's like a spiral of learning. And so let's clarify a little bit all that. So a supercomputer, one kind of supercomputer is an HPC cluster. An HPC cluster is an aggregate of computers, things that looks like computer. So now let's do a next experiment, a mental experiment, or mental test to understand a little bit what a supercomputer, how it is built. So imagine I assume that you are in front of a laptop, which makes things simple, or you are using a desktop computer. So you have like a monitor in front of you, a screen, and you have a keyboard right in front of you, and you have on your side, you have a mouse. Let's take all that out. You take the screen and you will be accessing the screen remotely. So you don't need the screen. Also, you remove the keyboard. Take the keyboard. You can, or imagine that you can take the keyboard and put it aside. The mouse, put it aside. What is left is the computer. You will be accessing this computer remotely. Now, to make a HPC cluster, what you do is to take a bunch of those, bare bones, it could be a tower, and you put all those in a rack. You put that in a shelf, if you want, or you just pile them somehow, and you plug them to the energy, and you will be accessing all those computers remotely. Each individual computer in the terminology of HPC of a cluster is called a compute node. It's just one individual computer. They have their own processors. It could be just one, it could be a couple. Usually for these kind of systems, they are dual socket. So they have two processors, two big chips for crunching numbers, for do the processing. And they have their own memory, and these machines could be accessed remotely. Somehow you access the machine. That is called a compute node. In the case of Thorny, we have more than 150 compute nodes. In the case of the new cluster, DALI-SATS is more modest. They have like 34, 37, I don't remember exactly. I think it's 34 actual compute nodes, and the others are specialized for something else. And so that's what we have. Those are compute nodes. Each one of those is a separate entity in the sense that they can do processing, they have their own memory, they look like a computer. Now, inside the computer, we have like a chip, that is pretty much like the chip that you see here on the image. And in the case of our clusters, they are called dual socket. It means that we have two of those processors on the main board, the motherboard, main board, inside the computer. They have two of those, and in top of those we have a big mesh, a big tower of aluminum or copper aluminum, something that dissipates heat, because these pieces of metal produce a lot of heat when they are running. So, and on top of that, probably a fan or something to move all the hot air out of the machine. So that is a CPU, central processing unit. Yes. Inside those we have cores, but before that, what I told you before, this kind of processor, this, for example, Xeon, are processors meant to run on data centers, on places where first they are in high density, so they need to be resilient to survive on a relatively high temperature for an extended period of time. They are meant to run 24/7 and do processing 24/7 without degradation, or significant degradation for the lifetime of this machine. Could be around 5 years. They are also meant to be to support memory that is resilient to flips, to changes in. So, for example, to cosmic rays. Cosmic ray could get it. Those are very powerful radiation that could eventually change the memory locations from 0 to 1. So this kind of processors support a specialized kind of memory that correct those mistakes, and those mistakes happens. And there is an anecdote from an election where we use those election machines where some candidate received 4,024 votes out of nothing, just because a cosmic ray enters and put the vote, and the vote in that location, the one into that location, means 40,000 votes out of nothing. So this is critical, having this error correction in the memory. All those processors are beyond what you typically have on a desktop computer. Okay, a CPU core is just one portion of this processor. This processor has multiple cores. Today, they are multi-core, all of them. So starting from the 2000s, basically all CPUs are multi-core. That means that they have like a copy, those are like copy-paste of the same circuitry repeated 10 times, 20 times, written in these CPUs. Each one of them is capable of doing operations on its own, and that is what a core does. So having multiple cores give you more capability to crunching numbers with them. In our machines, most of them, they have 40 cores, so 20 cores each CPU. The CPUs are dual sockets, so we have two chips like this. We have two chips, each chip 20 cores, with all of them 40 cores per compute node. Okay, now there is another term that it could be confusing. It's called hyperthreading. Your computer most likely has something like this. It's basically a way from this CPU to tell this operating system that they have more cores that they actually have, with the hope that the CPU, the electronics in the CPU is capable of reorganizing more efficiently the operations in such a way that this live product produce a better efficiency. We usually disable hyper-threading in our machines because they produce negligible effects in performance. So when we say that we have 40 cores on a compute node, we really mean that there's 40 actual cores in the machine. Now, CPU frequency, it used to be back in the 80s and 90s, it used to be an indication of performance. Back in those times, you have one machine that is, let's say, probably a Pentium or Pentium MMX or something. That is Pentium Pro. That was the terminology from the 90s. And if you are 40 or something like me, you probably is familiar with that, with those terms: Pentium, Pentium MX, Pentium Pro, all that. And they have like 200 megahertz. And 2 years later, they were 400 megahertz. And after 2 years later, they have 800 megahertz, 1 gigahertz. And basically, you just discard the old computer because the new one was significantly more powerful, just because the clock speed doubles. That's no longer the case. The CPU frequencies have been stable, basically stable, around between 2 to 3 gigahertz during the last almost 20 years. They have not been growing. On the contrary, what have been growing is the amount of cores that we have inside those CPUs. So now we see machines with, instead of having 4 cores, they have 8 cores, they have 12 cores, they have 16 cores, they have 20 cores. So we put more cores and we keep the clock speed stable. There are reasons for that. I usually explain that it's basically thermodynamics. We don't want to overheat that. There are limits, physical limits that we can achieve with the processor before they start making mistakes, making errors, converting zeros into ones, because the heat is so high that it start making that kind of physical errors. So we need to keep the temperature. It means we need to keep the power down. So all that we can do is to put more processors or eventually use less energy. For using less energy, we need to do the processor smaller. At least all the circuitry, all those capacitors, we need to scale those down. So we need less electrons, let's say, to put it in a way, moving around, so we don't create so much heat in the system. That is, for gamers, there is another solution, is overclocking. So it's jumping, it's artificially increasing the speed of the processor, with the hope that that will give you some advantage in the game, or more frames per second or something like that. And it's not too bad if the machine make a mistake. It will probably not be so critical. And if it's critical, it's a game anyway. So that's overclocking. And there are other techniques for cooling, liquid cooling, and there are all sorts of things that you can do to try to keep the machine raising the clock speed and trying to lower the heat somehow. Now, another terminology is cache. I will go a little bit shorter with this. Is just an extra layer of memory that is in the CPU, and is very important. And it's basically the difference between buying a Core i3, Core i5, Core i7. Is all those cache levels. So that is special memory that is basically the last piece of memory that is crunching the numbers, is having very tiny amount of data, but it's with a very, very high speed, such that is capable of feeding the processor with numbers for crunching, for doing multiplications, additions, all that. That is happening with this cache. So I will probably skip this, and then go to the storage. The storage in our systems, we have like an array of hard drives, physical hard drives, and the data is written simultaneously on 3, 4, 5 of those drives, well, actually 4 drives, and with for several reasons. One, if one drive fails, we have all the data, so the data is resilient to the failure of one drive, even the failure of 2 drives. So when drive fails, we replace it. The data will be healing somehow. For the machine like this, that is important. In your computer, you have a hard drive, the hard drive fails. If you have a backup, good. Otherwise, I'm sorry, your data is lost. That's one thing. Another thing is storage volume. So we have like a system with 600, I mean, I don't remember exactly, but it's more than 600 terabytes of data available for storing the researchers' data. So that's it. Another thing is the network. So this kind of machines, I told you, is an HPC cluster. So it's like this. You will see this. This is how Thorny Flat looks like, and how Dolly Salts will look like. It's like this. It's just basically like the size of a big refrigerator. Each one of those lights you see here, the red lights, green lights, red lights, green lights, all those, they have at least one computer, usually 2, 3, 4 computers are on each level on it. And all of them are attached to a very fast network. That network is expensive. That network is part of the reason why these machines are so expensive, but that's also the reason why we are able to put those machines to work together to do things that are very difficult to do with a single machine. So that is called distributed parallel computing, and this machine is built with that capability from executing big jobs or intense calculations that cannot done otherwise. So the terminology for that is bandwidth and latency, that the ability to move a lot of data from one computer to another, and also to move that data so fast that even if the data is small, we don't have to wait much from moving even a small data from one machine to another machine, that they need to communicate somehow because they are working together on a problem. Those are our 2 clusters, Thorny Flat, 2 our main clusters, so Thorny Flat and Dolly Salts. We have we administrate another cluster for some people in HPC. It's a cluster for security purposes with some extra security stuff. It's a side cluster, doesn't belong necessarily to us. We administrate a little bit that machine. And Daniel is in charge for another machine that lives in the cloud. It's a cloud that is like a virtual cluster somehow. But real cluster are those Thorny Flat, Dolly Salts. Dolly Salts is still not operational. It's already here. But it's in the final stages of configuration. It will be operational in August somehow. And this is the cluster that we will be using, Thorny Flat. This cluster is located in Pittsburgh, more exactly in the Pittsburgh Supercomputer Center. It has 178 compute nodes. So all those towers here that you see here, they are called racks. Those are like refrigerators. A refrigerator, a bit taller, a big refrigerator. They have like 4 of those, I think, 4. And inside those racks, we have 178 compute nodes. Inside all those compute nodes, if you aggregate all that, we have 6,500, a little bit more than that, CPU cores. So each machine has around 40 cores. There are machines with 24. So doing all the math is around more than 6,000 CPU cores. And we have 47 GPU cards for applications that demand so CPU cards. And on the contrary, Dolly Salt is a smaller machine, but they have a lot of GPU cards, 150 very capable GPU cards. So that is a more specialized cluster in that sense. So dolly odds, and you see here the specs of the GPU cards for those who know a little bit. This is the reason why tomorrow we will be having another workshop. This more specialized on GPUs and applications that use GPUs. So feel free to attend tomorrow, same time, same Zoom link. And if that is interesting to you, feel welcome. And let's mention here, before I jump into the next section, a command line is what we use when you use an SSH client. We will be, instead of using the graphic user interface, which requires a mouse, you are clicking buttons and all that. Instead of using that, we use a terminal. It's much lighter. And if you know how to use it, it will be actually more powerful than start clicking here and there with a mouse. That is the command line. And for accessing the cluster, we use a secure connection. I told you that in the introduction. How you access the machine is through a secure shell. So we have here the internet, and you are connected to internet. So there is nebulous sort of machines that through SSH connect. Well, that's not actually like this. Is connect to our gateway. So the central IT machine, ssh.wvu.edu, and from that machine you connect into our login node in Thornyflat, and from there you submit jobs, and the jobs will run in one or several of those compute nodes. We have 178 compute nodes represented here with these blocks, and they are connected with an InfiniBand or OmniPath with a very high speed networking, and they have storage associated to it. So all those compute nodes see the same storage and can put data there and read data from. That is a little bit an overview of what a secure connection is and what it does. So if you succeed to connect to the machine through SSH, and I will demonstrate this in a minute in the next section for Open On Demand, you can execute this couple of commands. So execute this, type it as it is, lowercase, and hit enter. You will see some specifications of the cluster, or at least the head node, the machine, the memory. And finally, just to put this in perspective, oh, I made a mistake here. Let's go big and see this from a big perspective. High performance computing is one of the big hot topics of today. Big powers like the US try to be on the front line of these kind of machines. So you see here right now, the US has the fastest machine on the planet, the fastest supercomputer on the planet, that is called Frontier, and it's at Oak Ridge National Lab. And the machine number 5 is there. It's called Summit. Is the fifth machine, the fifth fastest, and it was the fastest machine in 2018. On the other side, for example, the Chinese, they have a couple of machines in the top 10, which is Sunway Tianhu Lite, number 7, and Tianhe 2, probably incorrectly, number 10. So you see big powers, they try to have these machines. These machines are what we call an enabler, a technology enabler. They don't per se give you an edge in technology, but they enable the discovery of other things, either technology or science. If you are researching on materials, you most likely will need this kind of machines for your simulations. If you are trying to get a more performant motor, you will probably need to do simulations before you actually build the motor or the exhaustion chambers and all that. And all those are very intense calculations that require supercomputers. Better crops, aerospace industry, all those things could be heavily computational demanding, artificial intelligence, for example, all those things. And so having those supercomputers is critical for the development and the innovation of big powers. And there is a report from this year from an Australian think tank. So it's not, well, it's not Chinese, it's not US, so it's, let's say, let's consider impartial, I don't know. And so they released a report, and they make like a list of 44 critical technologies. And right now, China is ahead of is the #1 in 37 of all those technologies. And the US is the #1 in what is left of that. The good news is that still here, the US is #1 in high performance computing. So it's something that is a critical area where the US is still the dominant power on this. They have the fastest computers on the planet, and the aggregated power of all the supercomputers in the top 500, at least, that is compiled or that is produced every 6 months. The US still has the most powerful, or the highest computational power among those clusters, even if China has more clusters in the list. So they are competing, they are getting close over the time, and I don't know, maybe this is the last time that I can say this, but still, US dominates this technology, at least 2022. So that we will jump into the next session, which is open on demand. The first and easiest way for accessing the cluster from the web interface. So this is the idea. For this, you only need to use this URL, copy and paste this URL on your tab. I will do that in a minute to demonstrate that. I will go into the material and I will actually demonstrate how you access the cluster. You will be greeted by this. You enter your username, you enter your password. After you enter your do authentication, your phone, so you put all your credentials and you land on this page that looks like this, or at least the top looks like this. This is called the on-demand dashboard, and from here you can open terminals or create interactive jobs, and I will demonstrate in a minute how that works. One example of those interactive applications that you can launch and you can start operating directly on the cluster is a Jupyter notebook, Jupyter session. So you go into interactive apps and you open a Jupyter session. I will show you that in a minute, and all the numbers and all the how you fill this one. And also you can open an RStudio session, which is another language, another application for programming, usually statistics, more specialized for data and statistics. We will demonstrate that. Those are two applications that you can use directly from the web interface. So you will be using the cluster without having to use any command line at all. You have also a file manager, so you can move data, you can see your folders and navigate into the data that you have on your cluster using this. And also you can submit jobs. We will demonstrate that in the session for tomorrow, no, for Wednesday, about job submission, how you can submit jobs directly for the web interface. So you can create like a template and start submitting jobs without using the command line interface. So let's demonstrate that in practice, how all this works. So you go here. I will probably copy and paste this. So the first thing is to go into this, put your credentials. And you land into the dashboard. So you can do that if you know, your account, your password, you can execute this. All of you can get into Open on Demand. So this is the dashboard. Let's explore a little bit what the dashboard offers to you, what you can do with this. So here you have the file manager. So all the applications, all the things are basically around here. So here is the file manager. You can see your files. I will show a view of those. You can upload files, you can download files. That's convenient for the small things. It's convenient for one image, one PDF, or one image that you need to download to put it on your paper. This is okay. You can use that. For big things, there is another application or another service that is called Globus that is more adequate for moving large amount of data. So more than hundreds of megabytes, it's better to use Globus instead of using this kind of application, this kind of icons or buttons here. Create new files, all that. You can do all that with the file manager. We will see this tomorrow, I think. Yes, tomorrow for the job submission, how you can monitor jobs on the cluster using this interface, or how you can create jobs. It's opening another window, separate window, for submitting jobs from the web interface. So this is for another day. And also, this is one thing that, it's opening this for some reason. It's opening this. Wow. It should be like this. In my case, it's opening a new window, so that's why you will not see it here. But here, when you click here, it opens a new window or a new tab if you configure to do that, where you can start typing commands, the command line interface that we will see in a minute. Let me see if I don't know what is not. And most importantly, you can execute interrupted applications. For example, here, let's kill this. Okay, a Jupyter notebook. Here we have some desktop applications, some like a virtual desktop where you can execute things there, a few others. MATLAB, you use MATLAB. There is one way here to run MATLAB, actually running on a cluster, and so you have, if you request the 40 cores, you have 40 cores to run MATLAB, and 90 gigabytes of RAM if you need it. So MATLAB is there, and Jupyter Notebook. Let's do with the Jupyter Notebook. Usually the first one is okay. It's the best choice. So I will be using a very recent version of Python, and I will be using a standby, which is partition. I will explain that later on. It's like a compartment where I would like to submit jobs, where I have the ability to launch a job, to do an execution, a standby up to 4 hours. So that will give me 4 hours of execution. When I am reaching those 4 hours, I just save my work. If I need, I can recreate another interactive job for another 4 hours and continue working. So for just a period of work time, it works pretty well. Standby, so select that. I will ask him for 1 hour. and I will be asking just select something like 1 or 2 CPU cores, because if everybody requests 40 cores, well, the first one will get in, but the other people will be waiting until will be basically saturating the entire cluster. So you request just 2 cores just for the sake of the experiment here. And I will not be using GPUs. The standby will not offer you GPUs. If you request at least one GPU will not work. You need to say 0 GPUs. And here, if you want the modern version of Jupyter, which is Jupyter Lab, select that one, Jupyter Lab, and forget about this. And launch, hit launch. It looks like this. So it will open here, this section here is waiting for a job. And in a minute, it will open my session. It will give me a button here to enter. You can have multiple interactive sessions. You can have interactive sessions with different kernels. So you can have Jupyter, and also in another session being running Rudder Studio, and another session being running something else, a desktop application or something. So you can have a variety of things running there. And in this case, I have just one thing, is Jupyter. And you click, this is open here. Let's see. It's open in a new window, so I have to come back and reopen this. So it takes a minute here, and you land into this. This is the Jupyter Lab. And from this Jupyter Lab, you can start a new, let's see if I have something pre-made something. Oh, well, I can execute this probably. Okay, so this is your test for Python. So you can start executing Python here. Let me see. I can start doing basic math or doing setting variables and doing some operations. All this is in Python. It's a language that we will be using on the third workshop in the interactive applications with Python. So you can start using this, executing I believe, well, I can run all this probably. It will execute the entire notebook. Here, I click here, it will execute the entire notebook. It will show me a few things here, and yes, importing here some packages. So those are very typical packages in Python. NumPy is for numerical operations, SciPy for scientific operations, special functions, Bessel, spherical harmonics, all those things, integration, all that is in SciPy. Pandan is for data analysis, for basically manipulating tables, like the kind of tables that you do in Excel, but this time from a programming point of view, from programmatically. Networksy for network analysis is there, and scikit-learn is a library for machine learning, a common library in Python. And matplotlib is the standard de facto for plotting, for the standard plotting, 2D plotting. And so I'm basically loading all that here. So I don't know if I would load this. Okay. And in this case, in Jupyter, you execute this with Shift Enter. Something like this, something very simple. So this is Jupyter. When you are executing this, this is happening on a compute node. The process is not happening in your computer. Your computer is just showing things. Everything is happening on one of the computers, one of the 178 computers in the cluster. So if you are processing something that is intensive, you can do it. It's not using your computer, it's using a remote machine. And you can operate with the machine, like you can save your job, you can export this plot into a file, and you can open the file manager and download the file and paste it on a paper. Okay, so that is you. Let me see. This one finish, and I don't know. Okay. Another application to demonstrate is this one. Is Jupyter, is RStudio. You select the most recent version. Usually is good. Let's say 1 hour here. Let's say 2 processor here, and I will be launching this. Notice that I'm still having this Jupyter session for up to 54 minutes. It will be long. When this hour expires, the job just is killed. And if you save it, it's okay. If not, well, in the Jupyter, it have to save every 5 minutes, I think. So you will probably loosen down. Same thing. It's launching on a separate window. So here. So now here I have 2 interactive sessions. I can actually monitor all those. Those are jobs, and I should be able to see the 2 jobs that I'm running right now. This one RStudio, this one is Jupyter. So this one here in jobs will show me all the jobs, interactive jobs, submitted jobs, all those are available there. And I can stop jobs, kill jobs just from the web interface. You can also do some extra monitoring on what they are doing, where they are running. So this is convenient for how you interact with a machine like this, where you typically are launching tens, even hundreds of jobs that will take a few hours, several days, even a week to execute or running. So you need some way of monitoring all that, what is happening, if something finishes, ready for you to, as a human, take care of the results and see and eventually submit more jobs and all that. So this is RStudio. What I'm doing here is with something else, with Spark. It's open. It's basically recording my last session. And this is for R. This is a different language, more specialized for statistics or data analysis or that sort of thing. So in some areas, in some research areas in bioinformatics, there's popular. In areas related with health science, epidemiology, all that, they could go into this one or some other applications similar like this for statistics, for biostatistics. So this is an alternative. So this is Jupyter. And the last thing that didn't work for me, and I don't know why, was this. Oh, now it's working for me. Let me see. Let me check. It's the terminal. But somehow it's frozen. Ah, maybe it's that. Oh, open new tab. I don't know why it's for sometimes. Anyway, I will demonstrate this in a different way. the second way, which is actually the entering into the shell. So this is how you work with the cluster from the web interface on demand. I will show you how you kill the job. So here I have this is a latest page. So I would like to kill those two jobs. If you just close the tab, the job is still running. The job is there. Here. This job will still run for the next 55 minutes and this one for the next 50 minutes. To delete the job and freeze the resource for somebody else or someone else to do it, you just click here, delete, and you just kill the job. So it's really simple, just from clicks here, clicks there, and you can operate remotely on a cluster, very simple. Now, let's move on. The next 30 minutes. It will be start with the command line interface. For this, let me see if I can do. I would probably do the whole thing. Okay. Let's start with this, commenting a little bit, lecturing here what it is. But the best part is when you actually do things, when you interact with the cluster. So the command line interface, it could be daunting, it could be overwhelming at first. You see, oh, this is super complicated. My main message here is that even if the command line offers you thousands of commands, those commands, the names of those commands are far from intuitive at first. The reality of the matter is that you only need a bunch of them. So just, I will say 10, and with those 10, you can do most of the stuff you need. You rarely need anything beyond those 10 commands. And so that is, I just resume all this with 10 commands, try to learn those and get an idea what they do, and that's it. So in the shell, we will be operating with something that is called the shell. The shell works this way. It will give you an icon or a tiny message or tiny piece of text that is called the prompt. Here, I symbolize this prompt with the $sign. It depends on how you configure your system, and mine is a little bit customized, so it's a little bit different. But yours will have your username, the name of the machine, and something like that. And there, you just type a command, type something. And in the first thing is that lowercase and uppercase are different things. So you need to be very precise with the casing. Usually commands, the Linux commands, the Unix commands, they're all of them lowercase. Commands receive arguments. Those arguments are separated by spaces. So the space here, so the command here is ls. We will see that in a minute. And you have to put in a space, at least one space. It doesn't matter if you put multiple spaces, but at least one. And arguments, those are arguments. Usually arguments have like a dash and a symbol and a letter and eventually an extra word that you put after that and another argument. They work like that. You type all those things that will execute something under some specifications given by the arguments, and you hit enter. The computer will do something with that. And when it finishes, it'll return back to the prompt, to this menu. And you can execute another command and get another answer. And this is the way you enter in communication with the computer. So you type a command, you get an answer, you type another command, you get another answer. The advantage of that is that one is light compared with a mouse and buttons or all that. Is from the computer perspective, it's just sending the command remotely, for example, and you are getting back on your terminal the answer from of that command. So it's simple. Also, later on, and that is the purpose of the last session of the last day, you can automatize that with scripts, and those scripts are sets of commands and procedures that will execute an entire operation, an entire a workflow of operations, one after another. So that is another reason that later on you can automatize a lot with the command line interface. Something that is harder. It's also possible to automatize that in graphic user interface applications, but it's hard. It's a different beast. It's a different thing. Another example that I always use. Imagine that someone asks you to put on a photo on the lower part of the screen, happy birthday and the date, something like that. So in that case, you open your favorite graphics application, whatever it is, and you open the image and you click here on a button and they opt for making a text, and you put the text, and that's it. Now, imagine that someone asks you, okay, here, good, you do it. You put the image, you put happy birthday and the date. Now I will ask you something else. I will ask you to do exactly the same, with the small difference that I now have 1,000 or 10,000 images to do that. Instead of, well, you can do it. You can open one by one and start putting the text. It's painful. In that case, it's when I say you are a slave of the machine. You are working for the machine instead of the machine working for you. You can use from the command line interface within an application, simple image magic, there are several, where you can do exactly that, taking 10,000 images, and for each one of them to put like a small message on a small icon, on a small something on one corner of the image, and the computer will execute that for all the image. And if someone give you another 10,000 image, all that you have to do is execute the same command for the next 10,000 images. That is the power of the command line interface. That is the power of scripting. Okay, good. Thank you, Daniel, for helping me with the answer. So message number one is that it gives you automatization, it gives you flexibility, it becomes powerful for you in the long run. At first, it's painful. There is a learning curve. And when you start with the learning curve, you feel like handcuffed. You feel, oh, I can do this easier in another way. I can open MATLAB and do this, and you can open something else and do it. In the long run, it will give you far more power. Another thing is, I will just give you 10 commands, and you will survive with 10 commands for most part. And at the end of the day, are the list of 10 commands. You can come back to this page and see. So let's start with the first two commands. And echo and cat is for showing messages on the terminal, is like this. Echo. And for showing the content of a file, we use cat. I will demonstrate this. So a text file, if it contains something, cat will show you the content of that. That the first two commands. I will demonstrate those commands in practice. Third command, PWD. It shows you your current working directory. So it tells you where you is in the tree. So working on a cluster, working on a system, even on a Windows machine, the way the computer for the human present the organization of data, the files is in files and folders, and the folders follow the metaphor of a tree. This is just a metaphor. This is just something that the computer present to the human, because it's easier for the humans to see that in terms of trees. The computer will work things in a very different way. They don't care about those trees for most part. They work different. But for us, we work on a tree. So we are somewhere all the time that we are on the cluster. We are somewhere on the tree, and PWD will tell you where you are. So you can move into another folder, a subfolder, and after you can move back, so you know where you are. And that is important because you can change where you are. And to change where you are, you use the command cd. That is our for command. So, okay, cd. So we are for. To create new folders, we use mkdir. This is the fifth command, mkdir. And to know, to list the files and folders on a given location, we use the command ls. We have 6. And we can delete folders. If the folder is empty, we can delete the folder with the command rmdir. We have 7. Now, we have this command. It's like a simple, apparently a stupid command. But in HPC, when you do this kind of thing, from time to time you need it. Is touch. Touch is a command that will change the timestamp. Will put the timestamp. It means the time when the file has been modified to right now. That's the purpose of touch, even without changing the content of the file. And for some reasons, you need things like this, and to just change the modification time, even doing nothing to the file. So now we have 8 with this. Now we can copy files or renaming files, make a copy of the file, so copy the file to a different folder. And for that, we use the command cp. We have 9. And finally, mv. So probably it never includes touch in the list. mv is for moving files. Or renaming files, moving a file from one location to another, or simply to change the name of a file, we use mv. And finally, so I think I never include touch in the list. And for deleting files or folders, we use rm. Oh yes, I use. Probably made the count, but they including touch here. So 10 commands. That's all that you need for most part to interact with the cluster. Now, this is what I will be doing. Let's see. I will be, okay. I will, for a moment, change the sharing here to this. Okay. Okay. Just for demonstrating the command line interface in the last 20 minutes that we have left, and how you access the clouds. I am on a Mac, so I will demonstrate that, how you use a Mac. In the case of Windows, I told you, you need to use PuTTY, or you need to use this mobile extern for getting an SSH client. So on a Mac, on a Windows machine, first thing that I will be doing is SSH, my username at ssh.wvu.edu. I will ask for my password. It will not show anything, so you are not seeing my password here. it will ask for my dual authentication. And I will be getting some. Okay. And now I land on this machine. This machine is the SSH gateway for WVU. This is the machine that allows you to get in from the network perspective, from the security point of view of the university. You are connected to a machine that is recognized as being inside the campus. This is the SSH gateway. You are not yet on the cluster. You are just on this gateway machine. The sole purpose of this gateway machine is to greet you, ask for your credentials, and give you this prompt here where you can jump, so we call it jump in, or make a connection, an SSH connection to one of our clusters. Right now, we will be demonstrating Turning-Flat, but the procedure will be exactly the same where Dolly sots became available. So SSH PF, this is one way of accessing the Turning-Flat, hpc.wvu.edu. SSH space, the space is important, not the number of spaces. Doesn't matter how many spaces you put, but at least one, and tf.hpc.wvu.edu. Hit enter. And now it will show a big thing here. This is all the standard legal message, and that you are accepting that you will be conducting research on this machine. This machine is not for gaming, it's not for anything else, it's for research, and we monitor everything, basically everything you do on this machine. So to be sure that you are abide to the rules of usage. And a few commands here. We will see this in the next session in 2 days. And that's it. So now let's review. Now you are in Turning. This is Turning-Flat. This is, and the purpose of this first session here is to familiarize ourselves with the command line interface, because the next session in 2 days we will be using this. Let me see if there is something here. Okay. Okay. So now let's start exploring. I will try to open this. Oh, okay. Okay. I will be working this one. So again, this first message here that is most likely different to you, because I customize this, is my prompt. This is the prompt. Here I execute commands, hit enter, the commands after executed return me back to it. One command that will execute, for example, is not in the list, but this is another command, is date. You just execute date, and it will tell you what time is it, what we have here, Eastern time. We have 15 minutes for this, and that's it. First command. Notice that when I execute the command, date, for example, it will not exist. Okay, it's a command that doesn't exist. If you put it uppercase, even if you change one single letter, it doesn't exist. It needs to be exactly as it's written. just date. And that's the first thing. Commands, for example, ls, this command, show me here what I have on my home folder. This is this location here. Where you land in what is called the home folder. This is one of the two places where you can put data as an user of the cluster. The home folder, where you have a limit of 10 gigabytes for putting data, 10 gigabytes only. And there is a scratch folder where you can have like 10 terabytes, 20 terabytes, maybe for a while. And so we have more flexibility on the scratch folder. But on the home folder, 10 gigabytes, if you hit those 10 gigabytes, you cannot create a single file or modify any file. And so pay attention to that. That is another command, for example, that show you that probably yours could be a slightly different, and I customize a little bit this, but it's basically showing the quota that you have. It's not super important here. So how much you're using from the cluster. But let's go back. Let's keep track with the commands. ls is one command. The same command could have arguments that will change the way the command works. Those are called arguments or options. And if you execute it with this extra argument, space l-al will show a long version of the file with more information about the sizes, this is called the permissions of the file, the owner of the file. They will show more data compared with this, for example. Commands have options, and they change the behavior of the command. Okay, now let's go into review in the last 10 minutes the 10 commands that we have very quickly. Later on, you can review the material, read on by your own, and see. Echo. So Echo will just show you whatever you type, it will show you on the screen on return back the prompt. That is one command that is very useful. It looks silly, but it's useful, and very, very commonly used. So for example, there are a few variables here. This is a variable, we will see that later on, that show you where, what is your home folder and what is your scratch folder. What is the location of the scratch folder? There's those two locations where you can put data. And the echo is showing the content of the variable. That's another purpose of the command echo. Now, also, well, this one, you can do operations. I would put in something like this. Well, probably you don't use it for this, but in scripting you use it. When you are doing a script, when you are automatizing things, this is the last stage. You eventually will type things like this. You can, well, not that stupid, but something like that, where you have variables and you are doing some things for iteration, something like that. So you can do all other things with that. And a file. I need a file here. Okay, a text file. For looking, just for showing a text file, you use the command cat. And I have here one small text file, I think, that is a submission script. Is something that we will see in 2 days, the next session. Is the kind of files that allow you to submit jobs, to put things to execute, not an execution of the class. So cat will show you the content of the file. Just to be silly, there is another option here that is called cat, or the tag, so cat on reverse, that I basically show you the file, the same file backwards. But I never included in the list, so it's It's okay. The first two commands, echo and cat. Another command, pwd. So it show me where I am in the folder. For example, this is something that I will demonstrate next. I think it's tomorrow. No, it's in 2 days. Yeah, this where I have some files, some scripts. So if I want to know where I am, I use pwd. Another way of seeing, for example, this, there is another command here that I'm not mentioning, is, for example, the command tree. We're showing you the tree of folders that you have. So tree, I never mentioned, I never included in the list. pwd, yes. So I can change into my Scratch folder using cd change directory, and now I am on my Scratch folder. So if I execute this, I am on my Scratch folder. Here I can create a test folder, and I can use, this is mkdir, and I can change into my test folder, and I can do something the same. So here, for example, if you hit just the first part of the name of the folder, and you hit tab, the tabulator, tab, that is in the top left corner of your keyboard, the tab, it will self-complete. This is an advantage, another reviews in that. And also, if you move with the arrow keys on your keyboard, you can go back and execute and review previous commands. All those tiny little tricks save you time when you are working from the command line. So prevent you from over typing things that probably are a few keys, key strokes from getting those and executed. So that's how you change directory, how you create another folder. I can, for example, create another folder inside this one. But if I try to create again a folder with the same name, it will tell me, okay, the folder already exists. It will throw an error because you cannot create two folders with the same name. Okay, so here I can see the list of folders or the files that I have for in a long version, including a couple of folders that are, let's say, hidden. Every folder that starts with a dot is hidden. Hidden in the sense that normally you don't see it, but it's not hidden in the sense that I give you any security that nobody will see that. That's not the purpose. It's just something that you probably don't want to see. You put a dot and you skip it. And the purpose of those two folders, or pseudo folders, or dot and two dots here, is that allow you to jump into the folder app, and one dot means here. So it's basically jumping into the same folder where you are. So test folder, and the dot move you up into the folder, up into the tree, and the dot is right here. Is the location where I am. That's the purpose of those two folders in Unix, Linux environments, including Mac OS. Now, you can delete a folder if the folder is empty. You can delete it. If the folder is not empty, you need to delete whatever is inside before you delete the folder. Or you use another command in the rm that will delete folders and files recursively until nothing is left. Okay, so now if you see, no longer, nothing is there. If you execute ls, nothing appears. Okay. Copy files. So Okay, so I will be doing this as mentioned there in KDIV, even, odd. So I am creating multiple folders like this. So I create 2 folders, and here I can touch 1. Let me see, 2, 3. I'm creating some files. Touch quickly with those names, and let me see, and let's add. So you see now I have a bunch of files with whose name is the numbers, and also I create those 3 files whose name are the letters, and I have here these 2 folders of even and that. So I can copy, for example, A and 1 into the folder even, and I can copy the folder 2 and B, for example, in the folder odd. And later I can realize, oh no, but that's not exactly what I want. So I can go and delete the folder. There's another command, R and A, or I can delete the folder 2, the file 2 and B from the folder odd. And now I say, okay, what I will really want to do is to move 1, 3, 5, 7 into the folder odd, because those are odd numbers, and I would like to move folders and files 2, 4, 6, and 8 into the folder even. Now I have all those folders. So now I have 2 folders and 3 files. Again, if you want to see from the 3 command, you have 3 files here, the folder even that contains the files 2, 4, 6, 8, and the odd folder that contains 1, 3, 5, 7. So that is what you can do with the command. So we review the commands mv, rm, and okay. So that's the purpose of all of that. Moving files, deleting files or folders. I cannot delete again even here because it's not empty. So there is another command, so I can do those 2 things. I can delete everything in even and delete even. So delete the content and delete the folder, or I can delete the folder odd entirely, including the content. So it will recursively deleting everything, even if some more subfolders, it will go and delete everything inside. So that is, we can wrap this with all those commands. I think simple. I have a few exercises here where you try to execute this and create. So I will show you a command here. It's like calendar here. ls CPU. This is from the previous session where I show you that you want to see which are the processors that we have in our cluster. This is the processor that we have. It's a Xeon Gold 6126 that has 12 cores per socket. And we have, in this case, we enable hyperthreading only in the head node. So yeah, threads per core. So we have hyperthreading enabled. The total number of CPU cores or CPUs is 48. Some people call CPU cores, some people call those CPUs. 48. So 48 real are 24. They are distributed in 2 sockets with 12 and 12. So that is the processor. Compare that, and this is the speed of the processor, 2.6 gigahertz. And lsmem is another command that shows you the amount of memory that the machine has. So this machine has 96 gigabytes of RAM. That is the amount of memory available for it. From that, there is another command that is called free, that it shows the amount of memory that is currently used. I think is in megabytes or in gigabytes. If you want to see that, the total amount of gigabytes is 93, roughly. From those, 14 are in use, 58 are free, and everything else are cached, or the system is storing files and things to accelerate the process later. So, and there is another thing that used to be important years ago, which is the swap memory, which is hard drive or storage mimicking memory for data file. So with this, we wrap. This is our first session. Feel free, regardless if you register or not. Tomorrow is a different workshop. Is the workshop on GPUs, applications with GPUs. So we will reviewing what is a GPU, what we can do with that, and a few applications, deep learning, and later on machine molecular dynamics. So applications where GPUs play an important role. And this is important because we just received our latest machine, our latest HPC cluster that is specialized with GPUs, 155 GPU cards. And so very performant cards for those kind of applications there. We have all those. If you have questions, we are saying we close the session, but I will be here entertaining questions from you. If you have some, you feel free to post questions, and feel free to enter tomorrow, same time, 10 a.m. to noon, same Zoom link, regardless if you register or not. You will be welcome tomorrow. Otherwise, we will meet each other Wednesday for the second session of this workshop, Introduction to HPC, which is the most important session, where you will learn how to submit jobs and how the cluster operates, the guts of the cluster for as a user point of view. So feel free, pose a question. I think how many? We have 21. If you want, just I don't know if you can unmute yourself and pose the question.
Hello.
Yes.